Recording. All right, so it's my pleasure to welcome Johannes Flake from University of Bonn. He'll talk today about Drinfeld centers and monoidal adjunctions.
Yeah, thank you so much. Thanks for the invitation. It's a pleasure to be here virtually and give a talk. So my topic today is two things. Once there's Drinfeld centers, and then there's monoidal junctions. And then I'll try to connect these two things and explain why I think this is interesting and useful. So before I start, I should also say that this is based on joint work, including on joint work with Nate, who is out in the audience, and also Robert Laubitz and Sebastian Posua. Okay. So the first thing I want to talk about is Drinfeld centers. So I put this name on my cover slide. So what is this actually? Uh, so there is always a slogan in the top right corner. So the slogan for this slide would be somehow we have something monoidal. We start with something monoidal. A monoidal category, to be more precise, and we want to associate to it something that is braided. So about why we should be interested in such a thing, we'll talk on the next slide, but let me just show how this is done first. So we take a monoidal category. My categories look like this. There's usually a C or a D. We have a tensor product, and then we have a monoidal unit, which I denote by 1. So for such a monoidal category, we can define the notion of a half rating for an object in that category. So we fix an object, say V, in that category. Then a half rating for this object is an isomorphism of functors from the functor tensoring with V on the left to the functor tensoring with V on the right. And it's not just any functor, so it's an isomorphism of functors. And also it should satisfy two conditions, two axioms, which I drew here. So there's some mini tradition in our group in Bonn that we always denote the commutative diagrams with a smiley. So whenever there's a smiley on the slides, this means there is a commutative diagram there. So we have two commutative diagrams here. One that involves just V and tensoring with V evaluated at the tensor unit. So from either side, we can do this, and we always get the object V back. So there are some canonical isomorphisms to V, and I want now that these morphisms commute with what I have rating now. So this is the first axiom. And then the second axiom, so here now I pick X and Y. So these are just placeholders. I mean, I want all of this to be functorial. So we can think of X and Y to be objects, but we can also think of them as placeholders, and then we can look at the functors resulting there. So when I have two other objects, I can move them past the V object that is fixed from the right to the left. Oh, and I actually just no, okay, that's actually the way I did it. So I can apply C, but then I can do it in two different ways for two objects. So I can first move the X past the V from the right to the left, which would be going down here in this diagram. And then I can also move the Y past the V. So this would be the second step in this diagram. But I can also just apply C at the object X tensor V, X tensor W, which is also an object in that tensor category, or in the monoidal category here. So this is also a possible way of moving these objects past each other. And now the axiom is that these two ways should be the same. So graphically, I can represent this using these diagrams, or this diagram on the right here. So I have two objects V, X, and Y. And I can first move the X past the V and then the Y past the V from the right. But I can also do it at once somehow. And this I can illustrate using these kind of fixtures here. So if I look at it like this, then it always looks like a braid relation already. It's not quite one, but it'll imply one, as we see in a second. Because now what I can do is I can collect all objects with all possible half ratings. So for each object, I take all the possible half ratings. And I define these to be the objects of a new category, where the morphisms now are just those compatible or somehow commuting with the half ratings. So this gives me a category which I denote ZC, which is the Drinfeld center, also the monoidal, also sometimes called the monoidal center of C. And there's a dilemma now saying that this is going to be a braided category. No matter what C was, this is always going to be braided. And the proof of this somehow is very easy. So I look at this left diagram. Of course, if you're not familiar with this, it takes a while adjusting somehow once eyes to these kinds of pictures. But what I can see here is that I have a crossing in the top left, and then a crossing in the middle row right, and then another crossing in the bottom left. So this looks like a 1/2 of a braid relation. And now what I can do is I can take the lower left crossing and all the strands going in there somehow, and now I can slide it through this upper strand. And that is just because I can interpret these two crossings, the two other crossings, as just C applied to the tensor product. But then this is a functor, so it's functorial, so I can move actually the function or the morphism through there. So I get exactly the other picture here. And somehow now I have proven if I now reinterpret these pictures again in terms of the crossings, I exactly get somehow a type A braid relation here. Okay, so this is how this works somehow. So of course, somehow by construction, this center is in a sense all I can do when it comes to adding a braiding somehow. I mean, I take all objects and I take all possible braidings. So it's not per se, it's not clear how C, the original category, is related to this new category. But for instance, I can observe that if my category C was already braided, so there are these like lots of categories we know from representation theory. They have, for instance, representation categories of groups. They have a symmetric braiding in there. So every object comes with a braiding already. So the entire category has a braiding. So in those cases, the original category somehow embeds into this new category. But even in these cases, there will be more stuff added, right? Because for individual objects, I could have possibly other kinds of half braidings that do not come from the braiding that is already pre-existing in the braided category. So it's not exactly clear what this relation is per se. But we'll see in some examples how we can think about this. Okay, so now I gave you this definition. We know what Drinfeld centers are. So why are we interested in them? So let me just very roughly give one application. So namely, we can use braided categories, certain kinds of braided categories, to construct knot invariants. So how does that work? So if I'm giving a knot, so here we have a nice trefoil knot. So first of all, what I want to do is I want to cut it open and somehow move it around a bit so I can turn any knot, like the trefoil knot, into a braid. So there are loose ends, but the loose ends are only somehow in two parallel lines. And then between these two lines, I have something that is a braid. So this is just pure topological manipulation so far. But now I can take an object, V, in a braided category. So now this could be any braided monoidal category, and translate this braid diagram into a morphism in that category. Or to be more specific, an endomorphism of a tensor power of the object V that I chose, where the tensor power is given by the number of strands that are involved in this braid. So in this case, I have two copies of V because I have two strands, and then I have three crossings here. So these would translate into three factors of the braiding. So I have this braiding taken to the third power. So this now is an endomorphism in that category, but it's not what I usually want as a knot invariant. So I have to assume something more about this category, something that is called ribbon. So now that I can take a trace. So this ribbon condition ensures that there is, we have notion of a trace inside that category. So of this endomorphism, I can now take the trace, and I get something that looks like a scalar. So it's an endomorphism of the unit object in this tensor or monoidal category. And in typical applications, this is even a scalar, just a number. And now, if I put these assumptions, braided and ribbon there, so then also it will follow that somehow this process, I mean, there were some choices in this process. So for instance, the way I cut this knot open and turn it into braid, and there is some choice there. There are different ways of doing this, but it turns out that actually this doesn't matter in the end. So this number I get here, or more generally this endomorphism of the tensor unit, it will be invariant under these choices. So there's really, and also it's of course invariant under what kind of representation for the node I pick. So this is even more interesting maybe idea here. So I might choose completely different projections for the same node, but the theory here will now ensure that I will get something that is invariant under these different choices. So this is something that is interesting because differentiating nodes is a difficult problem. And for instance, now if I take as my braided category, this the one I talked about earlier, or more specifically, I take a Drinfeld center of a representation category of a finite group. So I take Z of rep G. Then this procedure here produces something that is actually well known. It's something like untwisted digraph Witten invariant. So it's a well-known link invariant I can get in this way. And other Drinfeld centers will produce other knots invariants. So this is a good source for somehow these topological invariants. So this is one reason why one could be interested. There are other reasons, of course. So, but there are these nice problems and these nice applications of Drinfeld centers. The problem is that most of the time, or often, it's a little hard to compute the Drinfeld center, and then if there are knot invariants, to compute the knot invariants that are derived from this. So I want to explain a bit about how one can compute Drinfeld centers. So now we'll specialize to a very specific kind of monoidal category. Namely, we'll mostly look at rep G. So I fix a finite group G. So then rep G, this is a monoidal category. It's a little more than that. So it's a tensor category. But in particular, it's a monoidal category. So I can talk about its Drinfeld center. And it turns out there is some nice representation theoretic description of this Drinfeld center in this specific case for a category rep G for a finite group G. So I need some setup. So first of all, I want to define what is a Jetta-Drinfeld grading. So a Jetta-Drinfeld grading for an object in rep G, so for a G module, is a grading such that somehow the action on the graded slices moves them around according to the conjugation action on the group. So this is this Jetta-Drinfeld condition. So I'm formulating this now in terms of finite groups, but I just want to say, and also this will be useful later, so it is possible to reformulate all this in terms of, for instance, Hopf algebras. So there are Jetta-Drinfeld modules for Hopf algebras. So for this perspective, it's useful to slightly reformulate this condition, or even this datum. So the datum of a G grading, this can be recast in terms of a co-module structure. So on this V, so I just consider it as a vector space now, I want to introduce a coaction. So there's a linear map going into kg tensor V, which I'm going to denote it by this delta. And also I'm going to use this Swidler notation. So this might be a little confusing if you haven't seen this before. So an element V is going to be sent to delta V, which I define to be a formal tensor product, V minus 1 tensor V0. So when I write, maybe I should highlight this a bit. So this is somehow Swidler notation. By this notation, I don't mean that actually for any V, there is a V minus 1 and a V0. This is more like a sum. So this is just an abbreviation for somehow a summation over I for some tensor I and some element V0 I. But there, I can use this shorthand, which is this Swidler notation coming from the theory of Hopf algebras, that makes this a little more compact, this notation. And then the condition that is be a Jetta-Drinfeld grading, I can just reformulate it in terms of this map delta. So this condition that the graded slices are moved around according to the conjugation action, this just can be reformulated by this formula here. So delta of G applied to something. So there is an action of G on the module here. So this should be corresponding to this more complicated looking expression. So this is how the action of G should be on the grading. So the first component here should be by the conjugation. Okay, so I have this notion of a Jetta-Drinfeld grading. And now I can define a category of Jetta-Drinfeld modules. So this is going to be a category consisting of objects pairs of representations of G together with a Jetta-Drinfeld grading. And then the morphisms are those that preserve these gradings. So this looks like a very, or it might look like a very artificial definition now, but it turns out that it's actually useful. So this is actually, this gives a description of the center. I have an equivalence of the categories of the center of rep G and this newly defined category of Jetta-Drinfeld modules. And it's even possible to say more or less briefly how this equivalence comes about. So to any to any grading delta, I can associate this half rating C, which is just somehow given by an action of the homogeneous degrees. So if I have an element VW, what I do is first I switch the order of them, but then also I act on W with the degree of V. And this is somehow encoded in this function delta. And now this will give will actually give a half rating if if this delta was a Jetta-Drinfeld grading. And going in the other direction, if I have a braiding, a half rating C, I can associate it a coaction delta by just considering for any V the element V tensor 1 in the tensor product V with the group algebra KG. And now I can half braid this. So I get something in KG tensor V. And this, so now this formally looks like a coaction, and indeed it will be not only a coaction, but even a Jetta-Drinfeld coaction. So this is the correspondence here, and this gives a very nice description, very concrete description of the Jetta-Drinfeld center. Of course, it still looks pretty complicated, but at least we got somewhere. And now we can even turn this into a very, very concrete description. So we can even classify, in this specific case, so G is a finite group, and the characteristic of the field is 0. We can even classify simple objects in this category of Jetta-Drinfeld modules, and then by equivalence in the monoidal center. So how does it work? So first of all, we will define a class of Jetta-Drinfeld modules, which then correspond under this equivalence to objects with a half rating. And the objects themselves, I define them to be induced modules. So first of all, I pick an element in G, then I consider its centralizer, and then I pick a representation of the centralizer in this group. So I have as a datum a sigma in G and a U, which is a representation of the centralizer of sigma in G. Now what I can do is I can induce up the representation to one of G. So this gives me an object. And then on this object, I define a coaction by somehow this formula. So how does this formula arise? So the idea is, if I look at the element 1 tensor U, so this, if I specialize this G to be the identity element in the group, then I place it just in degree sigma. So this is somehow the starting point, and then if I now extend this using the Jetta-Drinfeld condition, then I immediately get this formula. So this formula just comes from what we saw here. It's still underlined. From this formula here, applied to somehow just the initial choice of putting U in degree sigma. So this will, by definition, be now a Jetta-Drinfeld module. Of course, there are some things to check. For instance, if an element actually, I mean, for instance, an element in the centralizer will be the same as H tensor U for H in the centralizer will be just the same as 1 tensor U, or at least 1 tensor H acting on U in this relative product. So here I have to use that actually these elements are in the centralizer, so they will not affect the grading. Okay, there are things to check. I won't do this now in detail, but you can even check this yourself, and you'll see that actually this is a well-defined thing. So, okay, maybe the takeaway here is that there is somehow a somewhat canonical structure of a Jetta-Drinfeld module on modules that are induced from certain subgroups. So this is somehow the idea here. So, but all this is classical theory. I'm just giving you some background here. And then the classical theorem tells us that, okay, in fact, we have constructed a Jetta-Drinfeld module in this way. It only depends on the datum up to some conjugation. So I can conjugate somehow, simultaneously conjugate the element sigma and the representation U. So this will not affect the object I get there. And in fact, if I now pick the U to be a simple representation of the centralizer, then I exactly get all the simple Yetta-Drinfeld modules. So this is now a full classification of Yetta-Drinfeld modules in the setup. And hence a full classification of the simple object in the Drinfeld center. Of course, this is a very specific situation. So somehow all that I told you about these finite groups and so on, this is very classical, and this is well understood. But this is a very special situation. So somehow what comes next is steps of generalizing this gradually. So we want to extend similar ideas somehow to a larger scope. And some starting point is some work I did a couple of years ago with Robert and Nate, and then before that actually even with Robert. So let me explain what our starting point there was, and then come to some more recent ideas. So we were looking at categories that are not like categories of question.
Yeah, can you back up a slide?
Yes. Yes.
Yeah, so what's known, like if you change the field to a characteristic field, for example?
So the induction procedure, it will still work. I think the problem is that the categories is not. I mean, I chose category characteristic 0 here because I want a semi-simple setup. But there are versions in characteristic P. I'm just. So probably you get something like. I mean, my guess would be that I get something like proj of this category. But yeah, Nate, did you say something?
You can do the same construction, but take let's say either a simple representation of the centralizer, and if you do set up, that'll be a simple object in this Drinfeld modules, or you can take an indecomposable module over that and induce that up, and it will be indecomposable in this.
Oh, actually, yes.
So it's pretty nice. It's all in terms of this representations of these centralizer subgroups. So it's and in fact, Sarah Witherspoon, it's a result of hers.
Thanks for pointing this out. Okay, I wasn't sure if it extends fully. So thanks a lot, Nate.
Thank you.
So, but so what we want to do now is look at categories that are not of this form. So they are not of the form rep G. So so let me say something about these other kinds of categories that are out there. So from this perspective, maybe the slogan would be that representation theory, like categories of the form rep G, they are certainly tensor categories, but there are more tensor categories than that somehow. And I can give you now the first instance, maybe the first instance of something that is not actually coming from representation theory, at least not in this stricter sense of the word. So to define these categories, we fix again a field and now an element also in the field, which we call T. And then, so now this is very briefly. So usually this goes in several steps, but let me just shorten this a bit. So we associate to this T a category which is somehow universal in that it's pseudo-abelian. So it has direct sums and it has images of idempotence. It's idempotent complete. It's also a tensor category, so it's k-linear, it's a monoidal category, it's rigid, and it's even symmetric. And it's defined by only two operations on a set of partition diagrams. So this is now a mouthful, so let me unpack this a bit. So first of all, what is a partition diagram, maybe? So a partition diagram is a combinatorial gadget that has a finite number of upper points, a finite number of lower points, both can be 0. And then it has strings connecting these upper and lower points. There is no rule actually on how they can be connected. So one point can be connected to any number of other points. The strings can cross, so there are no restrictions there. The only thing is that somehow the diagram, it's actually only an equivalence class of such graphical representations, in that two diagrams are the same if and only if they have the same kinds of connected components. So the numbers, I want to distinguish them by their position. The upper points have numberings and the lower points have numberings, so I'm not allowed to reorder these points. But now two things are the same if they have the same kinds of connected components. So for instance, if I drew such a diagram, or I drew such a diagram, so this is the same kind of diagram, right? Because these 3 points are connected, they are in the same component, and then the fourth point here is separate. So now I've explained what a partition diagram is. So now I define two operations on such partition diagrams. So the first operation is composition. So how do we compose two partition diagrams? So first of all, we have to require that the number of lower points of the first diagram, which is the right one in the usual order of composition, equals the number of upper points in the left diagram. So in this case, both numbers are 3. So if this is now the same, if these numbers are now the same, so I can now stack the first diagram on top of the second diagram. So I get a diagram looking like this. And now this almost defines a new partition diagram. If I just ignore now these middle points, the only thing is then I lose some information. So whenever there's a component like this that only has these middle points, now if I remove all the middle points and I only care about the upper and lower points in this diagram, somehow I lose the information of how many connected components were in there. So to keep track of this somehow, I introduce a factor of t for any connected components that I remove in this process. So any connected component that arises here by stacking the lower points of the first diagram on top of the upper points of the second diagram, I evaluate it to be t. So in here I see that this doesn't work on the purely somehow monoidal level. So here this has to be at least a k-linear monoidal category now, because here this t is a scalar factor. And so there's the second operation. So the second operation is just I take two diagrams and now I can stack them or juxtapose them next to each other. So this defines somewhat the tensor product functor. So the way I've defined it, this category has objects just somehow natural numbers, and then morphisms between two natural numbers, I mean possibly 0, but then otherwise natural numbers. And then morphisms between such two natural numbers are just k-linear combinations of such partition diagrams. I have these two rules, so I define a composition and a tensor product on this category. There are somehow crossings like this, so I can read these as partition diagrams as well. So this gives me a braided or even symmetric monoidal structure. And then I have objects like this, or morphisms like this, that looks like cups and caps. So these will define dual objects. So actually the first morphism here will indicate that the object corresponding to the 1 point is actually self-dual. And now, so I've defined somehow a k-linear, rigid, symmetric monoidal category. But now I want something pseudo-abelian. So what I don't have right now is the additive and the idempotent complete structure. So then now there is a next step where I somehow formally adjoin images of, or formal direct sums of objects. So now objects are not just numbers of points anymore, but they are formal direct sums, finite formal direct sums of these objects that pre-existed. So the natural numbers, labeled by the natural numbers. And then to any idempotent in the category, I also add another object, which is just the image of the idempotent. So this is some technical completion process, which is not relevant for what I'm going to talk about today. So let me skip this part. But so now you have to believe me that somehow this way I get a pseudo-abelian tensor category. So all this structure. And so the idea was we wanted to get something that is not somehow representation theoretic. So how do we get this? So it turns out that at least in characteristic 0 now, for characteristic P actually, I'm going to forward you directly to Nate because he did quite some work on this case. So in characteristic 0, at least, if the parameter T is not a non-negative integer, then it turns out these categories are semi-simple and hence abelian tensor categories. So these are what people usually call tensor categories. But they do not come from any group. They don't come from any Hopf algebra. So there is no fiber functor to vector spaces or super vector spaces or anything like that in characteristic 0 here. So these are some of the first instances of tensor categories that are not representation theoretic in the sense of the word. One can actually also prove that there don't exist fiber functors and groups corresponding to these categories and so on. And this is related to Deline's theorem and Tanakian reconstruction. This is another direction that probably I won't go into today, but let me just state it briefly. But then also, I didn't tell you what happens if this number specializes to a number, so to an integer. So actually, then it turns out that, or a non-negative integer. So then it turns out that actually there is a specialization functor, which is a tensor quotient functor. So this is a full, essentially surjective monoidal functor from this category rep st, but now t is the same as n, maybe. I should have said this here. So t equals n, or n equals t, maybe. To the actual representation category of the n symmetric group. So now there is a group, namely the nth one, the t's one. T is now in the range where we can talk about symmetric groups. And actually, this the category rep st it specializes to this category. So modulo some ideal. So there is a kernel of this. It's not a faithful functor, but I can also describe this kernel and somehow, in a sense, this rep st now has the information of all the rep Sn categories taken together. Because basically by just varying the parameter and then specializing, I get all the groups. Also, I should say that even this quotient is somehow universal quotient. Somehow it's a unique maximal semi-simple quotient in a certain sense. So it's very, this transition from rep st to rep Sn, this is somehow very canonical too. Okay, so but the goal was to get ourselves some categories that are not representation theoretic in some sense, and we found them. So these are them. I should also say that there are many more categories. So Deline himself, together with Milner, first previously defined categories that correspond to somehow rep GLT in a certain sense. So they interpret in a similar sense the representation theories of all general linear groups taken together, and even all the super general linear groups taken together. And then there are versions for orthosymplectic supergroups, so including orthogonal groups and symplectic groups. And there are, by now, we have lots of other examples. So there's families by Knoop. And then more recently, there are families of exciting new tensor categories actually discovered by Nate, together with Andrew Snowden, coming from oligomorphic groups. So in some sense, these are all the same kinds of tensor categories. In that they are tensor categories, but they don't allow fiber functors, and they don't come from classical Hopf algebras or groups or anything like this. And so this is somehow this is actually another interesting question that that my colleagues and me are doing some research in. But this is not going to be the main goal of this talk today. Okay, so we have these other categories. So now I can ask, what is their Drinfeld center? What is their monoidal center? So actually, this question we did answer. So there was the first project with Robert Lawquist, 2020. It feels like it's been even way longer now, but probably this was the publication date. So so we did find somehow objects in, well, we did construct objects that are somehow in the center of this category rep st, that are somehow uniform for the parameter t, and that specialize whenever the parameter t is now a non-negative integer to these modules or these Drinfeld modules or, that I described before. So remember, before I talked about these W sigma u. So these were these induced up modules together with their half rating or the Drinfeld co-module structure. And somehow the first thing we did was somehow interpolate those. So we gave a construction that associates to any n. So this is now, we take all the symmetric groups together, we pick some element in there, we pick some representation of a centralizer, and then we defined these objects that are in the center of rep st, the interpolation category, but that correspond to this choice of sigma and u for one choice of n. And it's such that somehow, if t happens to be n, the specialization functor specializes to the objects we constructed, the kind of classical objects in the center. And back then, what we did is was very ad hoc. So we somehow guessed the heft rating. I mean, we spent some time just looking at what the heft rating looked like. So heft rating now is somehow a linear combination of suitable partition diagrams. So it doesn't look like the heft rating for the kind of some rep SN categories at all. I mean, we kind of knew what the functor, the specialization functor works. So we could somehow, but it's not very, I mean, yeah, since it's not a faithful functor, there's no canonical preimage and not one that somehow extends universally across all T. So there was some guesswork involved there in finding these objects. But once we had some good candidates, we actually could prove sufficiently easily that these are indeed objects in the center, but by just using that some of the category is very finitely generated in a certain sense. So there is just one generating object, this point, and there are just these 5 morphisms, and then all other kinds of morphisms, they are just compositions and then possibly tensor products of these generating morphisms. And then later maybe linear combinations and direct sums and direct summands, but that's about it. So so this was how this proof worked. And then we talked with Nate actually in Norwich in England at some point. So he explained lots of things to us that we didn't know at all. So in particular, he had some very nice techniques for these interpolation categories that are completely different than what we had used before. And then we worked together and actually could prove that, first of all, somehow up to direct sums and summands, we indeed had found the previously constructed objects. But what we didn't realize previously, what we did realize with Nate together then, was that actually these are somehow induced up objects. So when we can reinterpret these objects that we had guessed, or at least not even all of them, some of them were just I mean, for correct choices somehow, but the correct or the better way of looking at these things in the center of rep ST turned out to be actually via induction. So somehow there is a way of inducing up to ST, this rep ST, this interpolation category, and then there is a procedure very similar to the one I described for the finite groups that actually use these objects. But also proving this was not easy. So we relied a lot on methods that Nate had developed that themselves relied on some ultrafilter realizations of rep-ST. So there's a way of connecting rep-ST via ultrafilters to these families of all groups rep-SN, I guess F. Oh, sorry. So one has to take representation categories, but then one has to also include positive characteristics now, because we know that these rep-STs, they won't always be semi-simple. So they cannot be somehow a limit of something that is always semi-simple. Sorry. So to account for the non-simplicity here, we also had to, I mean, Nate explained this, so we had to throw in these modular representing categories. And then somehow taking a limit gives realizations. Long story short, in a long story short way. And then these objects in the center, they can be understood as induced up objects. Okay, so now I've given you somehow, all of this was somehow the backdrop. So this was what we did until a couple of years ago. So there is a theory of these Drinfeld modules. They are connected to the Drinfeld centers, so they are some way of realizing it. And then there is somehow induction seems to play an essential role in describing objects in the Drinfeld category or in the Drinfeld center. Okay, but then basically we wanted to generalize this somehow. What is the general idea here? I mean, in these special cases we could make this work, but somehow we didn't see the clear picture there. And so now this gets a little more abstract, but I promise it has some use. So there is a reason we're looking at this. So I want to introduce another gadget now, which is again a little more abstract, which is called a projection formula. So we consider the following setup. So we have a pair of adjoint functors, G and F. So these are antiparallel functors. They are adjoint, G is the left adjoint, F is the right adjoint. But now G is assumed to be monoidal. So this is the special case. And monoidal for me always just means like strong monoidal. There are people who make different distinctions here. We have a strong monoidal functor. So now if these categories happen to be rigid, or even just close monoidal, but let's go with rigid because this works for most of the cases we're interested in. Then on this very abstract level, we get an isomorphism of, or two isomorphisms of functors like this. So we have somehow an action of tensoring with y on the f functor, which is given by the g functor. And also on the other side, so we have an action of x on the f functor, somehow given by the g functor. So I'm claiming that there always exist these isomorphisms, and I even can give you a proof here. So the way to prove this is we go via some Unita embedding. So we take three objects. So we take another one, z. Z is just a test object. And then we take some humps between these objects. So z was fx and the y. So this is the first thing I start with. So what I can do is I can first dualize the y and bring it on the other side. So I use the adjunction between tensoring with an object and tensoring with its dual object. Then I have an actual adjunction between f and g. So I can now move the f over here and turn it into a g. So these are the first two steps. But now G is monoidal, so it commutes first with the center products and then also with taking the duals. So I get this next step. But now I can move the GY star back on the other side, just dropping the star. So it becomes GY on the other side. And now I go back via the adjunction, so I get the FX GY. This is the last expression. And this is exactly the thing I claimed it would be isomorphic to. So this is a very, very general and very easy to prove idea. Okay, and similarly, this works if the adjunction was the other way around. So F and G being F being the left adjoint and G being the right adjoint. So again, we stay in the abstract territory for a bit. So in the same situation, G and F is an adjoint pair. So G is the left adjoint and F is the right adjoint. And G is again monoidal. There is somehow a structure induced by this monoidal structure on G on F. By the way, some of the secret example for representation theories, the example to have in mind is restriction and induction for finite groups, right? I mean, if you want, you can just think G is a restriction from a bigger finite group to a smaller finite group, and F is an induction going the other direction. So in the same setup, I'm claiming I get a structure on F. So usually the adjoint, for instance, the induction for finite groups, is not monoidal, but it is somehow, in some sense, close to monoidal. So what I get is a Lux, what is called a Lux monoidal structure. So what is a Lux monoidal structure? So it's a structure like this. So I have a morphism of functions f x tensor y to f x tensor y in parentheses. And how does that work? So I can do first go via the unit to fg of fx tensor fy. And then I can use the fact that G is monoidal, so I can move the G to the inside here. But then I can apply the co-unit and cancel the GF away, so I do get f x tensor y. And similarly, I get a transformation from 1 to fg1 via the unit, and then to f1 because G is monoidal. Okay, I should have set G monoidal here too, actually. So there's a more general version, but we don't need this at this point. So this is somehow almost a monoidal structure, but it's only Lux. So this is, we have this transformation between fx and tensor fy to fx tensor y, but this is not an isomorphism. It satisfies somehow associativity, but it's not an isomorphism. So this is some other point. There is also a notion of an oblux structure. So this would be a morphism from fx tensor y going the other direction to fx tensor fy, also satisfying the corresponding somehow associativity constraints. This would be called an oblux structure, and this will also be induced. So in this setup, the adjoint f, it's not monoidal, but it's both Lux and oblux monoidal. And more generally, we can observe that actually we only need half of, I mean, we have used the G is just monoidal, but we could have improved this a little bit. If G was just oblux, then F would be Lux, and if G was Lux, then F would be oblux. So via this adjunction, somehow, these two halves of the monoidal structure get turned into two halves of this monoidal structure, but note that again, so Lux and oblux structures on F don't have to be isomorphism. So in general, F will not be monoidal. In most cases, F will not be strong monoidal. Okay, so with this backup now, we can go back to our actual question. So we still in the same situation. So we have G and F in a joint pair. C and D are rigid, and G is monoidal. So in particular, by the second previous slide, we have the projection formula isomorphisms. So now we can use these projection formula isomorphisms to lift bradings from D to C. And actually, that is some of the idea now. We take something in the center of D, and we claim that we get something in the center of C. So how does it work? Okay, we have an object X together with a half braiding in D. So we take Fx to be the object which is now the induced upper object. And we want a half braiding of the form Fx tensor y to y tensor Fx. But what we can now do is just apply the projection formula. So this turns this into F of X tensor Gy. So now we can use the braiding in D to swap the order. And then we can go back via the projection formula isomorphism to indeed have moved the y on the other side. So this will define what looks like a half braiding, and indeed, this is one of the results we have there. This will be half braiding, and the entire thing somehow defines a braided Lux functor from the center of D to the center of C. So in this, so one of these problems with, I didn't say this earlier, but one of the problems with Drinfeld centers in general is somehow that they are not, I mean, so the slogan is they are not nicely behaved with respect to functors. So they're not functorial in a nice way. Here, of course, this is not the usual kind of functoriality, but in some sense, it's some version of functoriality. So I did even say this is a braided Lux monoidal functor. So just to give you an idea of how things can be proved. So just for the braided part, so the functor being braided would correspond to the outer diagram here to be a commutative diagram. So I have the Lux part and I have the braiding, and they should be commuting in this way. But now I can somehow insert these two middle objects here. I mean, if actually everything is a functor here, but let's say those are objects. So, I actually skipped this part. So, okay. So then, okay, the left square here, this is just my definition of the braiding on objects of the form fx. So this left square is just how I define the C on f of x. The right square here, so this is just a naturality. So I have a C, and I have the co-unit applied in the inside here and there, going to the top right and going to the bottom left. But then this is just functoriality with respect to this co-unit morphism. So it remains to see that somehow the top triangle and the bottom triangle commute. But actually, I had this on the previous slide, so without saying it, actually, I just realized I skipped this. So the way we define these Lux and the Lux structure, so that is actually the reason I had this entire slide. Okay, this is kind of embarrassing. So this is the reason I had this entire slide, is that the Lux structure that is induced here is compatible with the projection formula. So I can replace, or I can read the Lux structure also as a version of a projection formula followed up by a co-unit. And somewhat the idea is here, this is indeed true. I mean, formally this diagram makes sense, but the point here is that it's also a commutative diagram. So in particular, the top and the bottom triangle here do commute. So we get a braided Lux monoidal functor. Now this is somehow an abstract interpretation of what we did in these papers with Robert and Nate. But of course, this is way more general somehow. So, but we can even say a little more. So this is just somehow the fact that one can induce up objects, but then we can ask somehow what is the structure of these, for instance, the structure of this functor ZF. So to say that, I have to introduce another gadget, which is that of a Frobenius monoidal functor. So remember, we had functors, for instance, these functors that were left adjoint to a strong monoidal functor. there are both Lux and oblux functors. So in case the Lux and oblux structure are not isomorphisms, those are not strong or monoidal functors, or just monoidal functors. But they can be something different, which is called a Frobenius monoidal functor. So this is defined by just reinterpreting the Frobenius law, which I can write like this, pictorially in terms of the Lux and the oblux structure. So whenever I have like a trivalent vertex like this one, I reinterpret it as an oblux structure. And whenever I have a trivalent vertex like this, I reinterpret it like a Lux structure. So then this Frobenius law, so reinterpreting the trivalent vertices here as somehow multiplication and co-multiplication of an algebra would define what it means for the algebra, for the bialgebra to be a Frobenius algebra. Reinterpreting it in terms of the functors tells us what is a Frobenius monoidal functor. So it's a functor satisfying this picture with these two replacements. So, for instance, every strong monoidal functor is Frobenius monoidal. And also, it is known that for finite groups, the induction functor is Frobenius monoidal. So we saw already that it's Lux and oblux monoidal, but indeed there is a compatibility between these two parts. And also, these Frobenius monoidal functors are interesting if one is interested in Frobenius algebras, which lots of people are, because by this axiom, they will preserve Frobenius algebras. So if I want Frobenius algebras in some category, I can take a Frobenius algebra and apply some Frobenius monoidal functor. And in particular, I could even take a trivial Frobenius algebra, like a tensor unit, that is always somehow trivially a Frobenius algebra, and apply this Frobenius monoidal functor, for instance, this induction, and I will find a Frobenius algebra in the target category. So it would be good to see if our functors that we produce now are also Frobenius monoidal. And indeed, this is the second result now. So in somehow the same kind of situation, but now assuming that actually the adjoint is an ambi-adjunction. So G is simultaneously right and left adjoint to F. We indeed get that the functor F itself, so this is just the both left and right adjoint, is Frobenius monoidal if, and now this is the condition, these two projection formulas, so from the left and the right adjunction, I get somehow two kinds of projection formulas of this form, in this line A, and two projection formulas in this line B. And requiring that they are the same, at least one of them will be sufficient for the functor to be being Frobenius monoidal. And the functor ZF, so this is the one induced on the functors, well, it is braided anyway, but it will be braided Frobenius monoidal. It is braided Lux and braided oblux under these assumptions anyway, but it will be braided Frobenius monoidal if A and B are actually the case. So these are some conditions in terms of the projection formulas that will ensure that the functors we produce here are Frobenius monoidal. Of course, in a braided setup, A and B are actually equivalent conditions. So somehow these two conditions coincide. Okay, so I had to hurry up a bit for the last couple of slides. So if there were more questions, just let me know. But I did come to my last slide for today. So now one can ask, where do we go from this? So one thing that we also did that I didn't want to cover today, one can now specialize back, for instance, to Hopf algebras. So we started basically from groups, or we could have started with finite dimensional Hopf algebras. This would have been almost the same idea there. But now we can take these abstract results and specialize back to representation categories of Hopf algebras. And one recovers, for instance, that the induction functor in the setup, so we have an embedding of finite dimensional Hopf algebras, is Frobenius monoidal, for instance, if H is semi-simple, or if both H and K are unimodular. So this is something a little weaker than semi-simplicity. And similarly for the center, it will be braided Frobenius monoidal. Well, the functor induced by the induction on the centers, it will be braided Frobenius monoidal if H is semi-simple and co-semi-simple, which, for instance, is implied in characteristic 0 by just saying it's semi-simple. So this somehow specializes back to the classical cases that, for instance, finite groups that we started with. Okay, and then there are questions, of course, now. So, for instance, in this concrete project with Nate and Robert, we found that induction from something somehow produce all objects that there are there in the center. So one of our results there was that if we take all these, so I didn't say this earlier, but the version of induction restriction for these interpolation categories, it looks like this. So we start with an interpolation category rep st, and then we restrict to something that is the lean tensor product of another interpolation category rep st minus n. So there is some natural number n, but this could be anything. With another just rep Sn category, classical representation category for Sn. So there is this restriction functor, and then it has an induction functor. And this is somehow how we got all the objects in the Drinfeld center, using this somehow monoidal adjunction there. And well, in these cases, it turns out that this produced everything there is in the center. Now the question is, can this somehow be proved more generally, or at least in certain situations? We don't know this at this point. And then there is another question, namely, one can actually go back to these. So this is something that I mentioned. So all these interesting families of tensor categories that are somehow similar to rep st. The point is, in most of these situations, we don't have a theory of restriction and induction, but actually, so also with the same people, Robert and Sebastian. So we did, at least for some of them, develop a slightly more general theory of restriction. So those are namely those are the categories coming, or in some sense, related to these cobordism categories. So there are just as I explained earlier, these categories that have partition diagrams of morphisms. Now one can add genus to the connected components in these partition diagrams, and then one gets something that looks like a cobordism. I mean, one can even read it as a cobordism. And then for the composition now, instead of evaluating every connected component to just a constant, one can actually vary the constant depending on the genus of the cobordism that is being removed there. So this yields a family of categories studied by Jovanov Sastanovic based on these cobordisms, and then they somehow specialize first of all to rep st, which is what we considered here, and then also to rep ot. So those are the interpolation categories for the orthosymplectic groups, and also other interpolation categories are somehow closely related to this one. And then basically for these kinds of categories, we have a version of restriction. For some of them, we also have a version of induction. So this is a little harder because showing somehow that these adjoints exist in the way we want them to, this is seems to be tricky. Okay, so this is just what we're working on right now, or what we have been working on right now. So I think my time is up already. So thanks a lot for your attention.
Yeah, I think there's like modular representation theory for finite groups. And I think Ron thought about this before. So we take a module and one compare it to it or not from a subgroup. And certainly it's going to depend on the support layer. And I think we have some work on this. Yeah, I think that's very, I'm not sure exactly what. It involves like looking at things. For example, these item problems, module construction. Right. So I'm just wondering how that might tie into what you're doing.
Unfortunately, I didn't get the entire question. So you were talking about finite groups, and yeah.
Yeah. So in the modular case, there's been some thought about when a module can be induced from a subgroup, and so John has actually worked on this And it involves looking at these idempotent modules. These internally generated modules. I think it involves centralizers too. I don't know. I
So
can-
when you say idempotent modules, do you mean? I mean, what do you mean? Do you mean like these Rickert kind of idempotent modules,
Yes,
or?
exactly.
Ah, yes, okay.
Yeah, so these are use that construction. So, I don't know, I can send you the reference. I don't know if it has anything to do with this. Oh, yeah.
It sounds interesting. Yes, yeah.
Other questions? If not, let's thank the speaker again.
Thank you.